Hi everybody, Professor Jamer here. So today we're going to talk about gravity, which is covered under Chapter 6, Section 3. So if we have a box resting on the surface of the Earth, we know that there's the force due to gravity, which is going to be equal to mass times the gravitational constant. But where does this G come from? So if we were to look at the Earth itself, here we have Earth. We know that the Earth itself has some sort of mass. The mass that is going to be equal to 5.98 e to the 24 kilograms. And Earth also has this radius RE, which is equal to 6.37 E6 meters. So we know that Earth itself has a mass and it has a radius, and we can kind of picture it as a circular object in space. So if we were to think about everything in the universe, there's going to be a gravitational pull between every single object and you. So if you're sitting next to a person, you two have a gravitational pull to each other. And we can talk about that gravitational pull as F sub big G, which is equal to big G, the first mass, times the second mass, divided by the displacement between those two masses. So this big G right here is the gravitational constant of the universe, and it's 6.67 e to the negative 11 Newton meter squared divided by kilogram squared. So this is the gravitational constant of the universe. And if you ever wanted to figure out how that was solved, you can look up something called the Cavendish experiment, where Cavendish was a scientist who had two big lead balls in a huge room, and he was able to measure the gravitational constant of the universe. And it's actually a pretty interesting study of how simplistic it was, but I definitely recommend that you look that up in its own time. So if I have an object on the surface of the Earth right here of unknown mass m, and I have it being pulled towards the center of the Earth, well, the Earth is also exerting a gravitational force on that object, Fg, and it's pulling it closer to it. So here we have Fg minus mg is going to be equal to 0 because the object is no longer moving. So then we can say F sub g is equal to mg. And so whenever we were to look at this a little bit further, we can say we have the g times the mass of Earth times the mass of your object divided by the radius of Earth squared is equal to the mass of the object times the gravitational constant of Earth. So here I have 6.67 e to the negative 11 times 5.98 E24 divided by 6.37 e to the 6 squared is equal to G. So when I calculate this whole left-hand side, what I wind up with is 9.8 meters per second squared is equal to the gravitational constant of Earth. So this is where the gravitational constant truly comes from. It's from this interaction of big G, and the interaction between every single object in the universe and whatever planet it is on, if you were to look at it from this point of view. So it is really important to realize that this force due to gravity is an attractive force. That doesn't mean that, so here this attractive force is pulling the object on the surface of the Earth towards the center of the Earth. If we were to look it out in space, and we have here's the sun, and then here we have the Earth, we know that there's going to be an attractive force between the sun and the Earth. And we draw out the displacement between the two objects from the center of the object to the center of the other object. So this whole distance even though we do have a radius of Earth and the radius of Sun, this whole distance that we measure for this problem is going to be r. So here, the force between the Sun and the Earth is going to be mass of the Sun, mass of Earth, divided by the distance between them squared. So you can calculate that as long as you know the mass of the Sun and the mass of the Earth. So if we wanted to find the gravitational constant of another planet, gravitational constant of Saturn. So we need to know the mass of Saturn, which is equal to 5.68 e to the 26 kilograms, and the radius of Saturn is 60,268 kilometers, which we need to convert to meters, and we want to figure out the gravitational constant of Saturn. So here we would use the same idea as we did before. So here we place a mass of unknown mass on the surface of Saturn. And here we have the radius of Saturn, and we know the mass of Saturn. So we would say the mass times the gravitational constant of Saturn is going to be equal to g, mass of Saturn, mass of unknown object, divided by the radius of Saturn squared. So the gravitational constant of Saturn is going to be 6.67 e to the negative 11 multiplied by, so here we see we have 1, 2, 3, 4. So we have 6.03 e to the 7th meters for the radius of Saturn in terms of meters, divided by 6.03 E7 squared, multiplied by the mass of Saturn. And when we plug that into our calculator, we get the gravitational acceleration of Saturn is equal to 10.41 meters per second squared. So that is how we can solve for the gravitational constant of any planet. And that's where our gravitational constant really does come from, because while we know that if we were to drop an object and then we were to time how long it takes for that object to fall, and we know the distance it falls, we can calculate g. But this is where g truly comes from, is this interaction between two masses and the displacement between them. So this is topic 17. Thank you so much for paying attention, and let me know if you have